Okay, so get this in order. Okay, there we go. Okay, so now we're going to change over completely and start talking about surface-based analysis of MRI data. And so this is something that I have been working on for a long time. We started this about 30 years ago now. And so if you use FreeSurfer or one of the other programs for doing surface-based analysis, this will sort of describe how FreeSurfer works, but many of the other the programs, there's only a couple ways of doing things, and so they sort of tend to be relatively similar to each other. But before we start, what we want to say is like, why do surface-based? So one of the things, so how does our data, come out? So typically our data comes out as a 3D block of data. So there'll be, here's, a coronal section of the brain, and then basically it's just a 3D block of voxels like this. And so that's basically your raw data. And what do you do with the raw data? Well, if you're just looking at one person, you could just sort of, stick with that coordinate system. It's an XYZ coordinate system. But typically, we want to, find the same place. Now, there's a good question, like, what is the same? Does everybody have the same place? That's a good question. Maybe they do, maybe they don't. So, same place across brains. And why do we want to do that? Well, we might want to, say, find an area, a particular cortical area. Find a cortical area. And we might want to average across subjects. Average across subjects. So back in the day, how did people start off doing this? They basically just smushed a brain into alignment with another brain. So some of the early methods that were developed for doing surgery, sometimes they're just called Talairac methods. That was just a guy's name, French neurosurgeon. And the idea there was they were just trying to sort of figure out, we're going to look for a tumor, or maybe try to remove a tumor, or put an electrode in and damage the place where the tumor is to try to get rid of the tumor. And we want to sort of go to the right place, go to the same place. And so that was the origin of the method. And there's all different kinds of versions of this. It's called, you could sort of Talairac a brain or align a brain to an average brain. And how does this work typically? It might, work by, generate average target. So maybe hand align a bunch of brains and then average them. Generate average target. And then blur single brain, because the average target is going to be a little blurry. So blur single brain, and then align. And there's all different kinds of ways of aligning it, aligning brains to each other. So some of them just use like a 4x4 matrix. And that, we could call that an affine transformation. So what can you do with that? That's not a very powerful kind of a transformation. That's just a multiplying by a 4x4 matrix. And what it can do is it can rotate and scale. And translate. The 4x4 allows it to translate. We talked about that back when we were talking about matrices. So it can sort of rotate things around. It can move them around to line them up in space in X, Y, Z, and then it can stretch in one direction or squish in another direction, but it can't bend. So if you do this, which is very common, you can't bend. So if somebody's brain looks like this, and another person's brain looks like that, it can't deal with that. It can't sort of like cause a bend in it. And so then there's other kinds of more complicated methods that allow bending, but you can see you can quickly get out of hand. If you allow too much bending, things can get quite messy. So why don't we just do this? And so here's one of the reasons why we might want to do that. So let's take, there's a couple reasons. I'll do it over here. So one of the reasons is that if you compare brains to each other, you can see that there's different patterns of major sulci. So here's an example. If you look at the superior temporal sulcus, you might, end up with somebody that has a superior temporal sulcus like this, and then it stops, and then there's a bend. There's a little sort of vertical sulcus behind it. And another person might have a superior temporal sulcus that goes like this, and it's got a little dent behind it like that. And another one might have one that sort of like bends down, and there's an upward dent. So what's this? So what is the problem? This is like, different pattern major sulci. So that's a problem. And what is the problem? Well, if you happen to be at this point in the brain, that point in the brain might actually be in a sulcus in the other person. So when you try to use a 3D method, what's going to happen is if you were sort of doing it perfectly, you would expect that a point here that's on the gyrus ought to actually correlate with a point that's in the sulcus. But then if you just go a little behind, you have a sulcus correlating with a sulcus. And so you would have to have your brain like taffy so that so one part of it could move a really long distance away, and then the other part not move very much. And it's hard to arrange something like that to allow a deformation, a nonlinear deformation, that is so flexible that it could line up a gyrus with a sulcus and yet not completely turn the brain into complete taffy and just mush the brain all up. So that's one of the problems. Why you would like to instead reconstruct a surface, and then if you reconstruct a surface, you could align the surfaces to each other. We'll talk about how you might do that, and that might be easier to essentially capture these two similar points in the two surfaces. So that's one reason. But another reason is the crinkles. So if you actually look at any sulcus, the way a sulcus looks, so like you look at the STS is a major sulcus, but it doesn't look like that. What it looks like is it's got all these little crinkles in it. So if this is a drawing of the banks of the superior temporal sulcus, if you look at any brain, you'll see that it looks like the sulcus looks something like this. There's all these little sort of like crinkles in the sulcus. It's just an unholy mess. And so what happens is the sulcus forms first, and then it sort of like crinkles up in a direction, in this direction parallel to the sulcus. And all sulci have these, but the problem with them is they're completely idiosyncratic. So when you look at one brain compared to another, the crinkles are completely different. And so what that does is that just mushes the data around and misalign. And when you use some kind of transformation matrix, linear transformation matrix like this, it can't capture all those little crinkling and bending. And even if you use a higher order one that allows more crinkling and bending, those crinkles might not be that relevant. So they're just like idiosyncratic. They just happen to crinkle here. And if you align them up, maybe that's not actually helping you. So that's kind of motivation for why you might want to do surface-based analysis. And the other, it's kind of an obvious thing. It's really an obvious thing to do. There's a lot of resistance to it over many years because it's kind of there's a little more work to doing it. But my entry into it was, it was in the days before, before high-resolution MRI images were available, and I had done work, neurophysiological work, where I would just physically flatten the cortex. I was doing it originally with small animals like a squirrel or a rat, so that I could get the cortex flat and cut a section parallel to the cortex. And then I did it with a human. Actually, I got some human autopsy specimens and just flattened them out. So I knew it could be flattened because I had actually flattened the physical brain itself. So what are the methods that we use? Well, one of the problems that we have is, so we talked about how we might sort of get some basic alignment, and we still might want to do that in order to sort of get some general idea of, where we are. But the next problem we have is normalization, and that's a big problem. So if you look at a typical scan, the error or the CSF error is going to be, say, like 3, and the gray matter might be, say, about 90, and the white matter might be, say, 105. So that seems like that's good. The white matter is brighter than the gray matter. But the problem is, if you're near the coil, this number could be 140. So you could easily have a 50% change in the brightness as you get closer to the coil. Now, if you look at that image, it looks okay because your visual system is really good at doing these local normalizations. But it's not going to cut it if you're trying to classify those tissues on the basis of brightness, because you're going to have to deal with, I've got in some other part of the brain, the value over here is 160 and 140. And so I've got to classify 105 as white matter, but then on this other part of the brain, I've got to classify 140 as white matter. Sorry, I did it wrong. So in this part of the brain, I've got to classify 105 as white matter, but in this part of the brain, I've got to classify 140 as gray matter. So you have to somehow flatten out the image. But how do you do that? Well, so one way you can do that is by something called histogram equalization. And this is one of the methods used in FreeSurfer. And what is that? Well, you just plot out a histogram of all the pixels in a slice. So you take a slice like that, and then we just plot out a histogram of the brightness of each pixel. So that's the brightness, and this is just count, how many. And so if you make a histogram like that, what will it look like? Well, there'll be a whole lot of 0, because there's the air outside the head, so there's a whole lot of 0, and then there'll be less of these intermediate values, and then on a good day, there'll be a little spike for, the gray matter, and then maybe, hopefully, it goes down, and there's a little spike for the white matter, and then there'll be some blood vessels up here, something like that. See, so that's a typical histogram that you would get of a slice. But the problem is, like, there's going to be some that look like this, where the slice was a lot brighter. There's going to be some that don't have this obvious difference between them. So the way histogram equalization works is you just look at the histogram and then try to figure out, like, where is the white matter based on, how many pixels there are. And so one thing we could do is just look for, ignore the bottom for a while, and then start searching for where you rise out of the background. And then say, that's what I'm going to multiply everybody by to make that number the same across slices. So that's called histogram equalization. It's a well-known technique in image processing. So that's one way of sort of flattening out the image. There's all different kinds of variations on doing that. So that's good. Now you could also do some kind of pre-scan. You could do pre-scan normalize, or you could do quantitative T1. That's another where we actually have a real number, so we don't have to normalize. You could divide T1 by T2. So there's other things you could do to try to help out with this. But for the most part, people are they might do pre-scan normalize and then just run it through the normalization program. That's 98% of what people do is that. Most people haven't done quantitative techniques as much, partly because they take more time, more inconvenient. Okay, so that's a good start. But now we need to sort of like get at the cortex, and so one of the things we need to do is to get rid of the skull. And so how do we do that? That turns out to be a little bit of a harder problem than you might at first guess. So what does it look like? Well, so here's the air. So the air, I'm using light to mean dark. So here's the dark air colored in. Okay, then you have a layer of skin. So here's skin. Then there's a bright layer of fat. So that guy's bright. That's some fat. Then you've got a really dark layer that's bone. So this is bone here. And then there's a little bit of a lighter layer, which is the marrow of the skull. So that's, there's some blood vessels and stuff in there, and that's a little lighter. And then you get out to the inner table of bone. So there's more. So basically, your skull is like other bones. It's got like a bony outer part, and then there's some blood vessels inside of it, and then there's another bony outer part on the other side. So here's more bone. There's more bone there. And then there's some CSF, which unfortunately has the same color as the bone. So there's some CSF there. And then maybe there's a little dura. And then finally you get into the actual cortex here. So here's the cortex. And so how do you just get the cortex out of that? So it turns out so here's that CSF going down into the sulci a little bit. So it's quite a mess. How are we going to deal with that? So this is something that Anders worked out way back in the day, probably 1991 or something like that, 1990. And so this is a method of using a deformable template. And this has been copied in FSL, so the skull stripping in FSL works the same way. So this is a method that people in sort of visual object recognition had used. So if you know If you know that all flowers have sort of a round shape, then one way of recognizing them is to sort of make like a canonical flower shape, sort of a typical flower shape, and then just try to squish that flower shape into alignment with something in the image to recognize a flower. And so we know that the surface of the cortex should be a relatively smooth surface. And so if we start off with something, so if we start off with basically a sphere, and then deform the sphere, we can end up doing a better job of finding a kind of a noisy boundary, because we already know what the shape is supposed to be. It's supposed to be a sphere, so then now all we have to do is just slightly deform that sphere. And so here's how that method works. So the idea is you start off with a sphere that's inside the brain. So we place a sphere inside the brain like this. So here's our sphere. These are some points, individual points on the sphere. And now what we want is a little core sample. So here's a core sample perpendicular to the sphere. And so here's a bunch of samples along the core sample. So we can sample the image. So what are we doing? So here's the image. Here's the image pixels. So we can sample the image with this core sample and set up something that basically keeps pushing us out until we reach black. So what we're looking for is black. And so the way this works is we have a force on that vertex, that single vertex of the surface, that looks like this. And so it's got some weight because we're going to have some other forces. So it's got some, so that lambda just says like how strong is this force. And then we have this normal. So here's the normal vector. So this guy is we calculate at each point, what is the direction parallel to the surface, and then we take a whole bunch of core samples, and we use this funny symbol, meaning basically multiply all the core samples times each other. And so we multiply them after we figure out the maximum. I know it's getting out of control. So the maximum of either 0 or a squashing function times the image value. So that's a pixel image value, and this pixel image value starts at the location of the surface minus d. So this is d here, that's the same d, for a whole bunch of different d's, times the normal vector of the center. Okay, so that's an actual sample point. So that's like, say, one of, so it's figure out like how bright is this at this d. So at this d, figure out how bright that pixel is. That's this thing right here, because this is the image value. And then we just subtract that from a target. So this guy is the, targ. And what is the target? Well, the target is black. So this make this guy dark. So basically the way this equation works is, for each time step, you move perpendicularly down away from the surface, looking for a bunch of sample points. You basically multiply them all by each other, maybe squash them a little bit, forget about that, but basically what the sample point is what is the brightness of the current pixel, and then I subtract off my target. And if the pixel is brighter, so if the pixel is brighter, like we're still inside the brain, then this is going to be a positive number, and that's going to push me out. So that will push me out because this whole thing will be multiplied by the vector that is perpendicular to the surface. So basically what will happen is that will just keep pushing the whole surface out until finally the surface reaches the black. And when it reaches the black, suddenly this function will say, we're just going to be 0, just turn off the force. The force will actually go negative, but since we have the max here, it just says, we just take, the max of either 0 or this function. If this function goes negative, then we just stick a 0 in, and then it turns off the force. So basically what will happen is the surface will sort of float outward from the brain until each individual vertex hits black, and then when it hits black, then it stops. Now, we need to somehow also keep the surface from collapsing, and so what we do there is we sort of look at, and we also want to keep the surface from getting rumply. So here's three little points on the surface. So here's, those are the neighboring points on the surface. So here's 3 neighboring, let's do a little neater one. Okay, so here's one point on the surface, and then here's another point, and so we'll put another point over here, and another point here. Okay, so these are all the guy's neighbors. So here's, you can think of this as a plane defined by the neighbors. Okay, so one last time. That one still didn't make visual sense. Okay, so here's a better one. So here's a neighboring vertex, and another neighboring vertex, and a neighboring vertex here. So I'm looking at it. And so here's the plane. There's the plane defined by the neighboring vertices. Now what we can do is we can look perpendicular to this guy. We can do some cross products and figure out, like, what's the normal vector. So that's the normal vector for that vertex. And then what we can do is 2 things. So one thing is, keep vertices unsquished. That's the technical term for that. So we can, whenever we move a vertex, try to sort of keep it the same distance from its neighbors. And then we can also try to remove, curvature. So try to keep the surface as flat as possible. So if the surface is kind of concave, move it up a little bit. So basically you'll have, if the surface is concave, move it up. If it's convex, move it down. If it's not distributed equally between its neighbors, move it in whatever direction you need to move it in order to sort of keep it the same distance from its neighbors. So if you do that, plus you also have this additional force that basically pushes the surface out until it reaches black, then you can end up with a pretty good stripping of the skull. So this is how these programs actually work down there. And they might, computers are fast now, so they could do this all in just like, a couple seconds. But that's actually kind of the guts of how it works. So you start off with a deformable template, a movable template, and then you plop it in the middle of the brain and allow it to expand outward by doing all these core samples until it finally hits hits some black, and then as soon as it hits some black, it completely stops. The reason you have to do extra core samples is in case there's maybe a little bit of black. There's black inside the brain. We have to sort of skip that, and some of the other core samples will help sort of like push it out. So, so now we've got rid of the skull, and so now, but we still have some problems, and one of the problems is there's often a little bit of noise in our data. So an example might be, here's a little bit of white matter right here. So here's gray matter and white matter. But what if there's a bad voxel sitting here that's just too dark? If that voxel is too dark, it might be classified as gray matter. Now, you might think, well, that's not such a big problem. We could just go and edit that one out. But the problem is there's 16 million voxels in a data set. And so unless you're pretty much almost perfect, you're going to end up with a mess. And so one method of dealing with that is to do an anisotropic filter. So what you could do is you could take a little block of voxels like this, not very many, say like 5. Did I do 1, 2, 3, 4, 5? I did 6, okay. So you could do a 5 by 5 volume, and go to each voxel and then look at its 5 by 5 neighbors. Okay, I got 5 that time. So 1, 2, 3, there we go. So take a 5 by 5 volume and then search through that volume to find the plane of least variance. So find plane least variance. So this is an anisotropic filter. And this is a crucial thing to actually make this work even reasonably reliably. So find a plane of least variance. So before I say this, why don't you just smooth the data? So you can do that. If you smooth the data, what happens is you reduce the resolution of the data set a lot by smoothing it. So you could get rid of this bad voxel if you just smooth it in 3D. This is basically a way of less smoothing. So find a plane of least variance and then only smoothen that plane. So how would that fix this voxel? Well, it would take a little chunk of 5 by 5 right here, and then it would say, oh, I detect a plane in this direction. And so I'm going to smooth in that direction, and then that will smooth it with some other white matter voxels, and it would kind of like get rid of that little bad guy. And like I said, there's 10 million voxels in the data set, so all you have to do is screw up on about 10,000 of them, which isn't that much out of 10 million, and you'd be editing for a month. So that's how so you actually have to be super accurate. So only smoothen that plane. And that will get rid of all these little speckly bad guys without smoothing your data, without really blurring your data, without losing resolution. Okay, so now we've got something that is pretty much just the white matter. So after we've done this, then we could just say threshold stuff below white matter. So anything that's darker than white matter, we get rid of it. And so now what we have is, here was where the cortex used to be, but now we just have this kind of eroded white matter glob. So now our data set just looks like this, just white matter. Okay, we got rid of all the gray matter. So now we finally are ready to make a surface. So how do we make the surface? So one way that you can make the surface is by basically doing something like the Photoshop paint bucket in 3D. So you probably, if you've ever used Photoshop or a drawing program, you have like a little paint bucket, and the paint, it goes back to make paint from the 80s. So you just click on something, and it fills up any voxels that are similar color, so that you can sort of so you can select a region, a connected region. So you can do that in 3D. It's a little more complicated. So say there's a ventricle inside there, and maybe there's like some little crap in the skull out there. Okay, so what we can do first is do the paint. Do the paint bucket in 3D. So this is paint bucket. That's the technical term for it, paint bucket in 3D. So I just put a seed in there, and then fill up the ends. Sorry, I'll leave this one blank and do it. So we start with a seed there, and then we fill it up. So what will happen? It will sort of fill up this guy like this. There'll be a void out here. It won't do anything to that guy. So it'll fill up that. Okay, so that's pretty good. But you've still got that ventricle in there. We don't want that. That's not part of the cortical surface. So then what we could do is, this is our seed. Start a seed out here. So what's that going to do? That will now, fill up the outer part. And that will get rid of this guy. But unfortunately, it will create another void. So now we fill this guy up here. Now we've got some stuff outside of the brain. So we got rid of that guy, but now we created one outside. So we do it again. So if we do it again, then we just end up with just a filled up. So we start another seed. So another seed. And do this again. And so now what we have is just a solid block of voxels. We've got a solid block of voxels. And so that's still not a surface. So how do we make a surface out of that? So what we have to do is we have to go through that solid block of voxels, which hopefully doesn't have any voids in it. It's just a single simply connected block of voxels, and then we've got to kind of tie it together into a surface. So let me just draw, let's just draw a little chunk of that. So there's one voxel. This is going to take a while, isn't it? Okay, here's another voxel. So these were voxels that were classified as white matter. So they were classified as white matter. All these white matter voxels there. So it goes off that way. It's quite a you can see you can get complicated situations here. Okay. Okay, so this is a connected block of voxels, and now what we want to do is figure out who the neighbors are. So we go to the boundary, go somewhere at the boundary between a filled voxel. So these guys are filled, and then the ones that are in front, sorry, that goes that way. Those ones are not filled, and then what we need to do is find all the neighbors. So just, there's a hairy program that will find all the neighbors. And then one thing we need to do is order them, because we're going to be taking cross products. So we need to order these guys, put them all in the same order so that they go around the same way. So order. And so now we have a surface. So what is the surface? So typically in a 3D in a 3D case, how do you represent a 3D data set? Well, it's just an image that has a value at each XYZ point. So this is a 3D data set. The surface data set is completely different. So a surface data set, it's part of the reason that there was kind of resistance to this is because the surface data sets are just so bizarre. But if you look in any computer graphics game or anything like that, how do you represent a surface? Well, you got two parts of it. So you have the vertex list. So this is like a list of all the coordinates of the vertices. So here's x, y, x1, x2, y2, z2, etc. So that's a long list of the vertices. They're usually implicitly numbered. So this is, vertex 0. If we start, here's vertex 1. So you leave those out to save space. But this doesn't say who's connected to who. This just says where's the location of each of these vertices. So at each intersection here, there's a vertex, and it's got XYZ coordinates. And so the vertex list just gives us those dots. It doesn't say who the neighbors are. So what do you need to find out the neighbors? So usually you have a face list, and the face list is also implicitly numbered, so like face 1, you don't put the number in there because who needs the number, because they're all in order. And so then what you have for the face is, what is the vertex number of that face, of the four corners of that face? So this is the surface format in FreeSurfer or any animation program that's using a surface. It will do something like this, or WebGL. So what are these? What are those things? Those are just the vertex number. So that it would be like the vertex, like for instance one of these guys. So it would be 1 there, even though we didn't bother labeling it to save space. Okay, so that's the format of the surface. And so when you look at this, it's just a list. So this thing is a 3D volume, but this is just two lists, basically. And so how do you use that surface? Well, you read it in, and then the first thing you have to do is this actually doesn't directly list the neighbors of the vertices, and so we've got to do some additional work. So when we read this in, the first thing we do is find the neighbors of each vertex. And then usually find the normals, because we want to light it, with cross products. So if we do a cross product, remember, is a way of finding out a perpendicular vector. So if we take this guy and imagine those things are vectors and then do a cross product, the cross product will stick out. It'll be perpendicular to both of those guys. And so then we can tell which direction that little piece of the surface is pointed. Why do we need that? We need that if we want to draw a brain, to make it look like a brain. It won't look like a brain at all unless it's properly lit. And in order to light it, here's the sun coming from the upper left, and here's the brain right here. How do we make it look like a brain in a computer program? Well, we've got to figure out, okay, here's a vertex right there. And that vertex normal is pointed in that direction. And so since the sun is also pointing in that direction, that one's bright. But here's another vertex, and this guy is pointed in that direction. And so when we look at the sun's direction of that guy, it's pointed in almost the opposite direction, so that guy is dark. And if you didn't do that, your visual system is so good at making shape from a shaded surface, you don't even realize until somebody drew a brain without the shading on it, and you say, whoa, it's just like it's a flat disk. I can't see anything there. So you always need to find the normals. So you would read this in, figure out who the neighbors of a vertex are, because this doesn't explicitly say it. It just says, who are the vertices for one face. But then you've got to, dig through it and figure out like which vertex number is a neighbor of this guy. There's going to be like 3 or 4 or 6 of them. So once you have that, now you've got a surface. And then typically what you do, this part is used for drawing. So this is, you need the faces in order to, draw the computer graphics image. But all the data is associated with the vertices. So we'll have a lot of data associated with the vertices. So there's a whole bunch of data. So there might be 100 different data values at each vertex. And what are these data values going to be? Well, they're going to be something like, last position, the normal, a statistic. You could have a time course associated with that. How deformed. They could be like a zillion different things associated with each, data at vertex. And how would we get the data, say like a statistic? How would we get it at the vertex? Well, we would need to, I'm almost done. We need to do something like this. So say here's a, let me tilt it. So here's a block of functional statistics. So here's a 3D block of functional statistics. So we've taken our time course, did the whole nightmare that we did in the previous thing, and we came up with an F ratio. And so we calculated the F ratio for a voxel. So how do we get it onto the surface? So now here's the surface. So here's the surface. And here's the surface. Now the surface doesn't have the same resolution as the 3D data set, so it might be finer typically. So here's our surface. These are all the vertices on the surface. So how do we get the data onto the vertices? And then here's another surface. This is like the gray-white matter surface. So how might we get that on there? So here's one way of getting the data on there. We find the surface normal. So here's the surface normal. And then we say go about halfway. That one's a little bit sort of, let's do it, start one here. So we find the surface normal. So this guy is perpendicular to the gray-white matter surface. And then we tick up there maybe about halfway the way to the peel surface, and then we say this vertex gets this voxel. So this voxel gets applied to that guy. And then we've got, our stat attached to a particular vertex. And so you can see that this is a different way of dealing with the data. You've got these lists. There's basically a list of, data at each vertex, and it's a different setup than here where you just have a simple three-dimensional volume. And so you can see it's a little more fiddly dealing with it, but there's a lot of advantages to doing this. A lot of advantages. You can unfold the surface, you can morph it into alignment with the other surfaces, which we'll talk about next time. And so I'll end there before I go way too far over and asked for some questions. So there's no class coming in, so we have some questions time. Okay, David.